So we are starting with Roman numeral 5 about defining acids and bases. So the first model, it's just what we've been using to define acids and bases so far. It's called Arrhenius's model, so it's Arrhenius, or the Arrhenius model of acids and bases. And this model is what defines an acid as something that contains hydrogen and will produce hydrogen ions when it dissociates in water, and then a base is something that contains hydroxide and will produce hydroxide ions when it dissociates in water. So this matches exactly with the definition that we've learned already of acids and bases. So Arrhenius's model says that an acid is a substance that contains hydrogen and ionizes to produce hydrogen ions in aqueous solutions. And then a base is going to be a substance that contains a hydroxide group and dissociates to produce hydroxide ions. So in this case, this would be an acid because it starts with a hydrogen and it is able to break apart into H plus and Cl minus ions. And then this one is considered a base because it contains a hydroxide and breaks up into a cation with a hydroxide ion also. So when we are classifying as an Arrhenius acid or an Arrhenius base, all we're looking at is the formula as like a standalone thing. So if you have an OH, I thought that was a shaker for a second. If you have an OH, that is a hydroxide group that's going to be a base, and if it starts with hydrogen, it's going to be an acid. So take a second and practice by labeling each of these as an Arrhenius acid or an Arrhenius base using that definition. All right, so on the first one, CaOH2, is that an acid or a base? What about HBr? HNO3, H2SO4, KOH, and LiOH. So it's really as simple as looking at the formula. If you have hydrogen as the start, so sometimes we see things like CH3 or CH4. I don't remember if we talked about this last time, where hydrogen can be part of a compound, but it's not starting with a hydrogen, which is kind of a red flag there. I would not call these acids just because they contain hydrogen, because those are covalent compounds, so they're not going to ionize in water. All right, then underneath this we have problems with the Arrhenius model. It does not explain the behavior of all compounds that behave as bases. So it can only be applied to reactions that do contain hydroxide. So for example, ammonia, which is NH3, will produce a hydroxide ion, but it doesn't contain hydroxide itself. So this reaction right here doesn't actually contain hydroxide on our reactant side, but it's still able to produce hydroxide ions. So on the next page, we learn another way to identify acids and bases based on the way that they behave. So if we flip over, turn the page, there is another model that we use to define acids and bases, and it is called the Bronsted-Lowry model. So it's Bronsted, Lowry. So the Bronsted-Lowry is a more complete model based on how acids and bases actually behave, or how they act. So we're going to talk about these in terms of where the hydrogen ion is going, where an acid is going to be specifically a hydrogen ion donor, or it will lose hydrogen ions, and a base is going to be a hydrogen ion acceptor, which means that it gains hydrogen ions. In front of what? This? Bronsted-Lowry. Bronsted. Is that what you were trying to read? All right, so for example, if I were to look at this equation up here, so on the previous page, so if you want to flip back real quick, actually. If I look at this as an acid is going to donate, meaning lose, hydrogen ions, and a base is going to accept, which is gain, hydrogen ions. If I'm looking at this reaction, if I'm looking at NH3 and I'm looking at NH4 on my product side, what had to happen for NH3 to turn into NH4? Did it have to gain a hydrogen ion or lose a hydrogen ion? So to get from this, my reactant, to my product,
Did it gain?
it gained, right? It had to gain. So this thing gains a hydrogen ion. Based on our definitions, what would that make this? What type of thing gains a base? So this would be considered my base. So that's what we were saying here, is that based on the Arrhenius model, this would not be considered a base because it doesn't contain OH. But based on its behavior, based on the fact that it's gaining a hydrogen ion, it actually does act like a base. And then H2O, this is just water, but we know that H2O can act as both an acid or a base, either one depending on its circumstances. So we could write H2O as HOH, or we could just look at it as H2O. If I were to lose a hydrogen ion, since this is already my base, I'm going to assume that this is my acid, but now we're going to prove it. It's going to lose a hydrogen ion. So if I get rid of a hydrogen ion, I'm left with OH, which is what I have over here. So this one then loses a hydrogen ion, which makes it an acid. And then we are also going to add on to that what we call the conjugate acid and the conjugate base, where the conjugate base is going to be what's paired with the acid. So you don't have to turn your page. We'll fill this in just a second, but just so that you can see what I'm talking about. Conjugate, we'll do conjugate acid first. Okay, so conjugate acid is the species produced when a base accepts a hydrogen, and the conjugate base is the thing that's produced when an acid donates a hydrogen. So if we go back up, when this acid gets rid of its hydrogen, the thing that it forms is this, which would make my OH what we call the conjugate base. And when my NH3 gains a hydrogen, the thing that it produces would be called my conjugate acid. And then we'll get more practice with this on the other page. So I just wanted to show this on that reaction so that you could see kind of in the same area that the Arrhenius model is really oversimplified. If you're just looking at the formula, you really need to look at how they're behaving to figure out if it's going to act as an acid or act as a base. So if I go down to the second page, kind of where we are, sorry I'm jumping around, but this is the last time. We kind of have our like skeleton example here, where X doesn't really stand, or X isn't an actual element, but it more stands for just any element that we could plug in there. If I have this element bonded to hydrogen, and then on my other side I have that element by itself, the way that it got from this to that is by losing a hydrogen. And specifically a hydrogen ion, that's why it has the negative charge on here. So what type of thing loses a hydrogen ion? Acid base, conjugate acid, or conjugate base? So basically I'm asking, what is this? How would we label it? How would we label this? Is it going to be your acid or your base? If it loses hydrogen. Acid, good. And then based on these definitions, the thing that your acid turns into, so your acid, if you lose hydrogen, that means you're an acid. And then when you have your acid minus the hydrogen, so once the acid actually does lose the hydrogen, that thing, the species produced when it donates its hydrogen, is called the conjugate base. So those two are paired together. So this X would be my conjugate base. Notice that in both of the conjugate cases, the conjugate acid and the conjugate base, they're both things that are produced, which means they will always be on your product side. So if you're looking at your reactants versus your products, on my reactant side, that's going to be the actual acid and the actual base, versus the product side is going to be what is paired with them, called the conjugate acid or the conjugate base. So if HX, whatever thing that is my acid, then what does that make water? The base. And the base is going to be paired with the conjugate acid. So if you gain H plus ions, you are a base. And if you have the base on your reactant side plus a hydrogen ion, then you are the conjugate acid. So the base and conjugate acid will be paired up, or the acid and the conjugate base will be paired up. So the conjugate acid-base pair says that every Bronsted-Lowry interaction involves these conjugate acid-base pairs, which consists of two substances related to each other by the gaining and losing of a single hydrogen ion. So if you are trying to figure out which one is the acid and which one is the base, the question that you're trying to answer is, where is the H plus ion coming from / going? Sorry. So looking at example 1, I have HF and H2O. So when I look at that right away, this has a hydrogen and so does that. So they could both potentially be my acid. You have to actually break it down to figure out where the hydrogen is coming from and where it is going. If I'm looking at this and I have F by itself and HF over here, this looks an awful lot like my example that I had up there, where this to turn into this had to do what? Good. So if this is losing a hydrogen, that would make it my what? Perfect. Oops. And the thing that it turns into, so my acid, once it loses the hydrogen, turns into the conjugate base. So that would be this, my conjugate base. And then H2O, if it's not the acid, would then be the base. And I can check it because, okay, my base plus another hydrogen, so H2O plus a hydrogen ion is going to be H3O plus. So gains H plus. And that would make H3O plus my what? Conjugate acid. All right, take a second and do example number 2 on your own. So try to identify your acid, your base, your conjugate acid, and your conjugate base. All right, how did you label NH3? This would be our base. Okay, so if it is my base, then that means it's going to gain a hydrogen. And if I look at this, what would it turn into if it gains a hydrogen? NH4 plus. So the base gains a hydrogen, turns into NH4 plus, I agree. And then what would I call that? Conjugate acid. And then my H2O must be my, it's my what? And then I'll draw this one, I guess, like that. The acid is turning into OH minus by doing what? Good. And then I would call this my conjugate base. Make sense? Okay. So you'll notice that in example 1, we called water a base, but in example 2, we called water an acid, and that's because it acted differently in each case. In one example, it gained a hydrogen, and the other example, it lost a hydrogen, and we ended up with 2 different things. So we call water amphoteric. Anything that is amphoteric is going to be something that can act as both an acid and a base. So in example 1, water acted as a base, and in example 2, it acted as an acid. And then that is all we're going to do for this portion, but stay with us.